So today's class is going to be about learned representations, and we're going to kind of continue the story from last lecture and start to go into a bit more detail. So if you remember from last lecture, I apologize, it's a bit small. I talked about this idea of learning the scoring function. So something that can score the compatibility between an input X and an output Y. So for example, X might be some sentence or some document, and then Y might be some class, like is this a positive movie review, is a negative movie review, whatever you want. And then I briefly mentioned how you can, if you have a really good scoring function, you can actually form one of these probabilistic models by just making things, by just normalizing the scores, and then you can get a probabilistic model. And then I introduced these kind of three different ingredients. So parameterization. We could also use the word modeling. So this is basically what decisions do you make about how you compute this scoring function in the first place? Like what neural network architecture are you using? Do you have kind of different assumptions on the form and things like that? Then I talked about learning, so setting the parameters using supervision, and then inference. So in last class, we saw this kind of really simple example of a classification model, and it was based on this model called bag of words. And if you remember, it was kind of naive. It basically just like looked up the identity of different words and then summed them together. And then just briefly, we saw this algorithm. It was called structured perceptron. We won't go into that, pretty much anymore, but you saw it and it trained really fast, and then you can get a model at the end. And then to actually make a decision with the model, you use the simple strategy of kind of taking the highest scoring class. So that's what we covered last time. And then this time we'll kind of build this into something more realistic. So again, here we're going to still focus in this class on classification. And very soon we'll get to things like generating, full strings of text. And we're going to go over kind of three main things that actually turn out to appear in some form in basically any state-of-the-art system. So some of this might be a review, but even if you've seen it before, it's good to see again. And then if you haven't seen it, this is a kind of advanced class, so the class is going to go fairly quick. So definitely take time to spend more time on this after the course if it's not clear. And we also provide these kind of Jupyter notebooks that I won't have time to go through fully in today's class, but you can go through yourself to clarify things further. So we'll talk about what are called continuous representations of subwords, so rather than words. We'll talk about using neural networks. And then we will talk about the details of learning. So optimizing a loss function by taking gradients and using backpropagation and gradient descent. Okay, so yeah, last class we saw this bag of words, and as I mentioned earlier, I apologize I don't have the mouse here. I think there's some setting I have to activate. But anyways, so here for each word, we are looking it up in this vocabulary, and then you basically get this one hot vector. So everything is 0, and then you have a 1 in corresponding to the word position. And then we just add them up and get this feature vector, and then take a weighted sum. And we saw some downsides of this last time. So it's difficult to handle these conjugated words. It's you don't really have any notion of word similarity. So like with synonyms or things like that. And then it actually gets tricky to kind of combine multiple features together. So at the very end, you have this weighted sum, which might lead to some combination. but you don't really have this very sophisticated or rich combination of different features. Like if the word love is present and don't is present, um, and also taking into account the kind of position of each. Um, and then on the note about taking into account the positions, again, the bag of words just sums everything together. And so it gets really hard to kind of model the sentence structure. Okay. Um, so yeah, today we're going to talk about a few techniques that will allow us to overcome some of these. We'll actually need the sequence architectures like RNNs, transformers, things like that to handle the structure. So that'll be 2 lectures from now, something like that. Okay, so first we're going to go to the subword models and also the problem of tokenization. So here the basic idea is we want to take our different words and we want to split them into multiple tokens. So for instance, let's say we have this sentence, the companies are expanding. Then what we're going to do is we're going to use some algorithm, and the algorithm will give us this thing on the bottom. And it's basically saying that, okay, the word companies is actually going to be split up into these 2 different, they're called tokens. Similarly with expanding, it's going to split it up into these 2 tokens. So can anyone think of an advantage, just based on this very simple description? I didn't say how this works, but a potential advantage of splitting things up like this.
You get to share information whenever these subjects are reused in different contexts.
Yeah, exactly. So for instance, yeah, there's information sharing. So for instance, this ing at the end probably appears in a lot of different places. And so the model can potentially learn something reusable or shared about that. Similarly, expand might be in expanded, not just expanding. And so the model could potentially learn something about that and share information. Um, Also, when you think about it, suppose we have like the entire internet, and then we create this vocabulary. So vocabulary means set of all tokens. Let's say we create this vocabulary with every possible word on the internet. Um, then can anyone think of an issue with that? I guess maybe the answer's on here. Yeah, so basically, uh, here we have a vector, and the size of the vector is the um, size of the vocabulary. And so if you just take all these words, then this vector would be huge. Your vocabulary would be massive. And then any particular element in that vocabulary, you might not actually see that much training data for it. It might just be some weird word. And so this will, again, allow us to share information among a smaller number of tokens, and that'll also reduce the kind of computational costs. And so the core problem that is related to this, um, and you have to think about this like in, yeah, in state-of-the-art models too, is how you do what's called tokenization. So tokenization means you want to map this sequence of data or this raw data. So here it's some text into these discrete tokens from some vocabulary. Okay, so that process is called tokenization. You can also kind of detokenize in the sense that you might have these discrete tokens and then you want to map back to your kind of raw data form. And yeah, you can see here that there's multiple choices you can make. You could tokenize based on white space. You could do some kind of subword strategy. You could tokenize based on these individual characters. And when you think about it, there's at least 2 things that you want from your vocabulary or from your tokenization strategy. So the first thing you want is that you want to be able to represent any text with your tokenization strategy. So can anyone tell me an issue with splitting words by this white space in between words.
Many languages don't have spaces.
Exactly. So many languages don't have those. So most of the time you would just get an entire token for a whole sentence or something like that. And then similarly, you might not want to do something specific to even natural language, because nowadays we want these models to work on code. We want them to work on basically like anything we, copy and paste into ChatGPT. Um, and on the other hand, you want it to be very efficient. So you don't want it to be too large. I already discussed this, because then you'll have to store this really large vocabulary and learn about each element. But you also don't want it to be too small. And we'll see an example of this in a bit. What can happen is, let's say here you split on each character, then the length of your sequence gets really large. And so this could require a lot of computational costs then to kind of process the sequence. So in practice, you want to find something kind of in the middle. Um, and we could take a look at how some actual language models do this tokenization. Not like the algorithm that they use, but just the kind of results. So here's this cool website, if you haven't seen it before, called Tick Tokenizer. And so up here, you can look up these different models. So like here's the GPT-4 model. We'll go over this if you haven't seen this before later. But this is basically the formatting that you use to get it to be a kind of chatbot. But then you can type different stuff like, I don't know, advanced NLP is awesome. And so what this is showing you here is how it's being tokenized. So you could see this word advanced is turned into just one token, and it's the number 63,663 in the vocabulary. So you can see they have I mean, their vocabulary is at least, I mean, assuming they have all the numbers filled in, then you can get a sense of the size of the vocabulary, and you can get a sense of how things are being tokenized. So an interesting thing is like 1, 2, 3, 4, 5. So different models will have different ways of tokenizing numbers, especially. Maybe they do something where they tokenize up to 3. So just as an example, let's take a look at this model. So you can see here it's much different. Here they chose to only tokenize each digit individually. And so this is a kind of rule that they probably hard-coded into their tokenization strategy. So anyways, you can kind of see why this is important. It's basically determining what will the input be to our machine learning system. It determines the length of the sequence. It could determine, yeah, kind of differences between how different numbers are represented, things like that.
Why example? So the first 3, 4, and 5, I think each one, they are all in 0 tokens, right?
Hmm.
But the second time the 3, 4, 5 shows up, it's a full token.
Yeah, so I think it's just the color is deceptive. So I think they're still individual. Because this one is 29946, and then this one is 29945. Yeah. Okay. Yeah, see then this one is something different. So anyways, yeah, this is definitely something to know about and be aware of. And so the question is, how do you actually do this? Well, first, what you could do is start with the most, so I mentioned having an expressive vocabulary. That means you can represent anything, and one that's efficient. So one strategy is to start off as expressive as possible. And basically the most expressive thing you can do is to represent text as what are called UTF-8 bytes. So basically when you write text, like here we have Japanese and we have some English, then these will at first be represented as these Unicode characters. But then there's a lot of different Unicode characters, right? There has to be like one for each different kanji in Japanese, each English, and whatever, like any language that's supported. And so the size of the number of Unicode characters starts to grow. So then basically what happens is each Unicode character will be translated into these bytes. And so each individual character can actually be represented as between 1 and 4 numbers that are between 0 and 256. Okay, so you can actually go into Python and do this. So here you can see this text, and then we're encoding it as UTF-8, and then you can print out the different numbers. And you can see for this kind of simple string, it turns into this really long sequence of numbers that are between 0 and 256. So kind of cool. And the issue again, though, is that this will result in very long sequences. And so we want to now try to make it more efficient. So the key idea that's used in a lot of these different tokenization methods that are even used for the state-of-the-art models is called byte pair encoding. And the kind of core idea is very simple. So what you do is you have some training set of data, and then you go over and you look and you count up each consecutive pair of tokens. Um, so like here we have, let's say we're using just like English letters as I'm talking through this example. Then here you would have H is next to E, E is next to L, L is next to L, L is next to O, and so on. And so you count up the different occurrences of these characters. And then you just select the pair that is occurring most often, and you introduce a new token to represent that pair of tokens. Okay, so for example, here it turns out that the most common pair is actually E plus a space. So you could see that like the word here ends in E and then there's a space. And that turns out to be the most frequent. So then what we'll do is we'll introduce some new token. And now we can represent E and space as just one token instead of two. Okay, so it kind of reduces the sequence length, but it increases the size of your vocabulary. And that's really the key idea. So then you start with this kind of base vocabulary. You run this algorithm, it'll keep finding the most common instances and doing these replacements. And then it'll start to build up this vocabulary of kind of new combined tokens. So I won't have time to go through the whole notebook here during this lecture, but in the course code repository, there's a notebook that goes through this in detail. And it's actually based on this video. I don't know if you've heard of Andrei Karpathy. So yeah, he's kind of a well-known researcher, and he also makes really nice kind of instructive videos that go into a lot of detail. So I went through and basically turned that into a kind of notebook that you can go through, and it'll go into a lot of detail if you haven't seen this before. And again, if you have seen it before, I personally find it pretty interesting. So here is an actual implementation of the byte pair encoding, where it's going through and counting up stuff. And then you can run it on this text. This was about the Osaka Marathon. Um, and it's kind of long, and let's see what you get at the end. So here it's just yeah, merging things. Um, and then I guess I don't have the, do I have things printed out? Yeah, I don't have this part printed out. But then here you can also look at these libraries that have implemented these algorithms. So there's a library called Tick Token, and it's released by OpenAI. And it doesn't have the code to train a tokenizer, but it has one to run the tokenizer. So what you can do is like back in the day, OpenAI used to release things like their models and their tokenizers. So here you can load in the GPT-2 tokenizer and actually run it. Um, Another one that's popular is called Sentence Piece. So this one actually allows you to train your own tokenizer. And it's actually pretty easy to do. Actually, in this next code example that we'll go into later, it trains its own tokenizer. So you could see here it's being called, and then this one's actually showing the different tokens that have been learned. And so you can see it learned to group together these yeah, these characters. Um, yeah, so you can see here. So what happens is I was basically training it on one document. So if you give it a large enough vocabulary size, then it'll actually overfit sometimes. Um, so like one, entire words might appear really often and they end up getting like a full token. Whereas if you run this on really, really large amounts of data, then the tokens will be kind of more split apart. But anyways, it could be pretty instructive to kind of go through and see how this all works. Okay, did anyone have any questions about this before I move on?
Stop merging, because if you keep on merging the tokens, they will get very big tokens. Like how do you know when to stop?
Yeah. Yeah, that's a good question. So I'm not aware of like all the different strategies that people use to decide, but what you can do is you can look at different models, and models will usually have vocabularies that are in a certain range. So like 50,000 or 100,000 or 200,000. So I think sometimes the decision is made based on computational cost. So when we talk about the language models later, it turns out that actually, I'll actually talk about this in this lecture. You have to store a vector for each item in your vocabulary. And so you want to consider like how large is this embedding layer or this lookup table. And that'll actually have a huge impact on memory. So sometimes the decision's based on computational reasons. Um, yeah, so hopefully that's helpful. Mhm. 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 Um, so a big thing is you want the tokenizer to be expressive. Um, so if it's not sharing information, let's say between like English and another language, then then your model is kind of losing some learning signal. And so if you really do have this like vocabulary where, bytes are being shared between different languages, then you can get some even transfer between languages. Um, at least in theory, Uh, so so it definitely can yeah, it can have an impact. Another area where you see a lot of impact is with numbers. Because the model can sometimes there'll be a token for like some really specific number, like 768, but not 767. And it'll lead to these weird like errors and addition and things like that. Um, so yeah, it can have a big impact on performance. And then the other thing is that this will be later in the course, but when you're really trying to scale up the models, then you really want to take into account how many tokens you can kind of train on in a given amount of time. And so then the sequence length matters a lot. So if you have a really long sequence length, then you're going to get through less data than if you have a shorter sequence length. So yeah.
Info is retained, so it's how expressive the tokenizer actually is. Like, do you train like a downstream model and say how well it performs? Like, what's the general population?
Yeah, well, I mean, one simple thing if you're like designing your own tokenizer is just to make sure that is just to reason through it and say like, okay, if I'm only using English characters as my base vocabulary, then I can't possibly represent like Japanese or something like that. So that's like step one. And then step two is, yeah, you probably have to use different diagnostics like the loss, the performance, and different benchmarks. And if you vary the tokenizer, you might see differences in some case. Hmm.
Um, so I have a question about choosing the token IDs. So is there like any kind of difference between like choosing another set of token IDs, or like is that left to the encoder to figure out in any case?
Yeah, so the IDs will just be used to kind of identify different vectors. So the choice of the IDs doesn't matter. It's more like what they represent. So whether they represent, a full word, a half word, things like that. Mm-hmm.
So normally for context windows, we measure in terms of the number of tokens in a context window. So how do you compare between different models, because they might be using different tokenizers? So like for example, ChatGPT suppose X number of tokens in its context window versus Gemini suppose Y number. So are those numbers really comparable, or
Mhm.
how do you measure that?
Yeah, yeah. So I mean it'll vary based on the tokenizer. So yeah, I would look at like what is being used for the comparison. My guess is when a company says our model supports this many tokens, it means with their tokenizer. Um, yeah.
So, purely based on the data, or like how do you infer which localizations you should go for? Is it just trial and error process? Or?
Yeah, yeah. So this one is this algorithm, byte pair encoding is a popular one. And so this one is really data driven. Yeah, it just merges based on these frequencies in the training corpus.
Yeah, this would probably work for English. But let's say I want to generalize, would I then think about using other tokenizers?
Yeah, so things you might take into consideration is like um so so for BPE it depends on the training data. So then one thing you can do is manipulate the training data. So, for example, if you have a particular language that appears 0.01% of the time in your corpus, but you know that your model is going to be, deployed to customers in that language or something, then you can upsample those in the BPE training data. Um, so yeah, one thing that's done is to kind of be careful about how, like, what data the BPE algorithm itself is run on. Okay. Cool. And then yeah, I talked about these numbers. So yeah, some of the models will just always split individual digits. Um, so oh, the larger point here is yeah, if you look through different papers and things like that, um, sometimes it's not fully data driven. They might have these rules for like different edge cases they found, um, like numbers and things like that. Um, so Okay, so as a recap, yeah, I talked about tokenization and subword models. And so now I'll talk about token embeddings. So here the idea is instead of representing words, or now I'll use the word tokens, as these one hot vectors, Now we want to represent each token as some dense vector or continuous embedding. So this means that now we have this vector of real numbers, and it's not sparse, so there's not a lot of values that are 0. It's just this vector of, different numbers. And so here the other difference is instead of having the representation be the size of the entire vocabulary, now we can define this embedding dimension, so the size of this dense vector, and it can actually be much smaller if you want than the vocabulary size. And so the kind of architectural way that this is done is to introduce what is called an embedding layer. So an embedding layer, you can visualize it like this, or you can visualize it kind of with rows. And it's basically this matrix, and each column in the matrix will be a vector for each vocabulary token. Okay, so like the first one might be the letter A, the second one might be the letter B, and so on. And then you can have this operation, which is like, okay, look up a given token index. So if the letter B is represented as the number 2, then you can look up the vector for that token. And then one thing to just be to know about, because you'll see this sometimes, is that this is equivalent to multiplying by this one hot vector. So here we start with the one hot vector, it's of dimension v. If we multiply it with this matrix, then you essentially selecting one column from the matrix. Okay, so yeah, that's the embedding model, and we'll talk in a bit on how you actually train, so how you actually set the parameters of these embeddings, so how you actually set the numbers. But now we can already imagine making a better version of the bag of words called continuous bag of words, or potentially better. So here now, what we do is for each given token, we look up in our embedding layer the vector for that token. And now we can just sum together these vectors, and we get this kind of continuous representation or dense representation of the sentence. So again, this is still kind of naive in the sense that it's just adding things together. And when you just add like this, it's discarding the order information in the sentence. So for example, if you flip the position of hate and this, that'll actually end up with the same representation as the sentence shown here. And then to kind of start adding to our vocabulary of these layers, another popular one is this linear layer. And so here we're saying that, okay, our representation is of dimension D, but ultimately we want to get scores for these k different classes. And so we have to do this transformation, which is k by D. And so that will be represented as a matrix, and we'll call that W. So again, W could be k by D. When you multiply that with this D by 1, then you get, k by 1. Then it's also common to add on this bias vector. So that's like after you perform the matrix multiplication, you could add on the bias. And then this gives you this linear transformation. Okay, so this goes by the name of linear layer. And so here, the different parameters that we'll want to learn are the embedding layer. So we'll want to learn, the red numbers at the bottom. We'll want to learn the weights, W, and we'll want to learn the bias. Okay, and then we can actually implement this in code. So here, this is implementing an embedding table, an embedding layer. And here, this isn't an efficient way to do it. But, or, there's probably more efficient ways. But here's just showing you, kind of convincing you that you can do this one-hot multiplication. So here again, we have this a vector and, sorry, matrix. One dimension is the vocab size, one's the embedding size. Then to actually look up, that'll be this forward function. We'll look up a position x in the embedding table by multiplying this one hot vector, which is what I showed you before. Okay, and now in practice, this embedding layer is implemented in libraries like PyTorch, and they probably do it, in the most efficient way that we know about. Okay. So then we can actually implement the continuous bag of words model. And so now we'll have this embedding layer, and then we'll have this linear layer, we can call it the output layer. And then here you can see the forward pass, so performing the computation. We start with our tokens, embed them, sum them up. Then you have to make sure things are, in the right dimensions. And then you apply this output layer and ultimately get scores for each output class. Okay, let's see. So this again will be in the course repository. So again, if you haven't seen this before, yeah, I mean, you'll need to be familiar with PyTorch, things like that. In homework 1, you'll have to implement parts of a language model and be pretty familiar with PyTorch. So if you haven't seen this before, then definitely take some time to kind of get up to speed or refresh yourself if you haven't seen it for a while. And then if you have seen it, it's kind of fun to go through this. It's yeah, it's kind of fun to just train the small model on your laptop. Pretty satisfying. So here we're doing this sentiment classification, and it's with tweets. So here's like different tweets. Some of them might be offensive. I don't. It's not me who created the data set. I don't remember. But anyways, then each tweet has a label. So either positive, negative, or neutral. And then this is kind of cool. We're actually training our own tokenizer on this data set. So here's some tokens that you get. And then this is showing loading the data and actually implementing this model. And then you can train it. So I'll come back to this part because we'll talk about the loss function in a bit. So first, one kind of hope with these continuous representations is that now we can have some notion of similarity. So remember, this was like one of the downsides of the previous model. Now, like at least in principle, suppose that you could have some algorithm which encouraged two vectors to be close together in this continuous vector space, if they're kind of similar in some sense. And so here, this assumes that maybe you have some, huge data set, and different words are used kind of interchangeably over the course of looking over all the data. So in one sentence, it might use the word great, and then in a similar context, it might use the word excellent. And so, yeah, as a result, the vectors may be pulled close to each other. So I think we'll actually look at a numerical example of this at some point I think when we're looking at language models, to convince you that this can happen. But empirically, sometimes you do see this where, yeah, if you look at kind of nearby vectors, then they end up being kind of similar to each other after running the learning algorithm, close to each other. Okay, so that was the token embeddings. And so next we'll move to the neural networks. So any questions on this part?
Yeah, so the previous slide, you to the previous slide. How can, so I think in the approach that we mentioned earlier, we were summing the vectors, right?
Hmm.
So the wouldn't that aggregation kind of make this kind of visualization kind of noisy and like, or so like my question is, if we have enough data, does that addition operation kind of get overwritten through that much data, or with that plus we'll still have a noisy graph?
Yeah. So I mean, one thing to keep in mind is we're going to run some learning algorithm which sets the numbers for these different vectors. And so it could be possible that even though you're summing, the signal gets, back propagated to the individual vector, and then similar ones end up having some similar representation. Yeah. Yeah, in other cases, the kind of structure of the sentence will be more clear and easier to kind of reason about, but yeah. Okay. Okay, cool. So yeah. Yeah, I'm ready to move to deep learning. I think I've had enough with the really simple models. So next we're gonna so so next we're gonna talk about neural networks. And here one motivation, I mean this is just one, is that what we're gonna be able to do is basically stack these different layers together. And that will let us take advantage of kind of combinations of features. Or as the kind of information will propagate through the network, it can make kind of richer and richer representations. So if you think about like the first back-of-words model, we had to rely on just this final kind of weighted sum to try to take into account like negation, for instance. Okay, and so by introducing these multiple layers, we'll be able to yeah, take into account these combinations of different features and kind of transform them over time. So here we have a model which is called deep continuous back-of-words. And so here we're going to start with the same model as before, same architecture, just on the bottom. And then we're going to introduce this layer here. And the key difference is we now have this function which is called tan h. And the other key difference is that we are kind of stacking these layers one after another. So here, for instance, we have a notion of like the embedding dimension. So here it's visualized as 4. So we start off with this vector of 4 dimensions. And then we have this layer, which is this linear transformation again. But then it passes through this tan h function. And this is called the activation function. Then this can change the dimension if you want. So now we have this dimension RD. And then we can just keep stacking layers if we want, and maybe just keep the dimension the same. You can also change it if you want. Then again, you have the same output layer or linear layer at the end, and ultimately you get these different scores for your different classes. So does anyone, before I show the answer in the next slide, does anyone know why, ignore the stacking, for instance, right now. Does anyone know why this tan H is kind of interesting or what it might add to this architecture?
Without it, it's just like one big matrix multiplication.
Yeah, exactly. So this tan H, the specific choice of tan H isn't too important, but the important part is that it's non-linear. And so these introduce kind of something new into the architecture, and they actually make it more expressive. So as was mentioned here, if you don't have the nonlinearity and you stack these these linear layers together, well, then that actually is just equivalent to a linear layer. And so your learning algorithm can just basically you almost, treat it the same as if you just use one layer. However, if you introduce this nonlinear layer, then again, it gets more expressive. It can represent a kind of wider class of functions. So here's a kind of a nice visualization where it learns this kind of decision boundary, and it's a circle, and it might be difficult to learn that otherwise. But anyway, so this is yeah, a really important part of the neural networks and the deep neural networks. And nowadays we have a lot of different activation functions. You'll see some, I guess, in detail when you do homework 1 and you're implementing the language model. You'll see what activation function they're using there. And a good way to see it is just go on PyTorch and see which ones they have implemented in PyTorch. That typically means like, people are using it. Okay. So that's that. And so now it's actually the code doesn't change that much. So now we have here, this is just a simple one. So we just have one layer. It'll be this linear one. And now you could see, oh, there's a comment, new addition. The only new addition here is you have this torch dot tan-h and then the linear layer. Okay. But the interesting thing is, if you look at the results, so we'll talk about the loss in training in a bit, but if we just jump to the results, then here is the accuracy that you get with the this was the simple bag of words, and you get what, 71% validation accuracy. If you use this continuous bag of words but without the deep layer, then you get 72 or 73, a little bit higher. If you use the deep continuous bag of words, beautiful, 94%. So you could see here, of course, you could argue that, maybe there's differences in the training setup, but I made a reasonable effort to try to get the best performance that I could. But you could see here that even just introducing this one layer with the nonlinearity lets you have a much better system in the end. Okay, so that's kind of fun to go through if you want to see it for yourself. And you can run it on your laptop if you have a reasonable laptop. Okay. So yeah, so now you can learn things like I mean, you can't really interpret everything that the model's learning, but you could kind of reason about, in principle, what could it learn. One thing it could learn is, feature 1 and feature 5 are active. And so in the next layer, that's going to be one number. So that's like combining two pieces of information. And then when you stack that, now it can learn maybe some like higher level thing on top of that. Okay, so that was a really quick introduction to the deep continuous bag of words. And so now we're going to go into some detail about training the neural network models. So here at a high level, the strategy is to use gradient descent. So what we're going to do is we're going to write down a loss function, or gradient-based optimization, I guess would be more general. We're going to write down a loss function. Then we're going to calculate gradients, or kind of, derivatives of the loss function with respect to the model's parameters. Then we're going to move the parameters in the direction that reduces the loss function the most. Okay, so that's the kind of high level idea. Again, the goal is to reduce this loss function, and you do it by kind of calculating these gradients and then adding them to the parameters. So an example loss function, I'm going to go through two here. And I'm introducing these two because this cross entropy loss comes up all the time. It'll be not the binary, but the cross entropy will be used to train even like the large language models and things like that. So it's really good to be familiar with these and kind of get an intuition for what's happening. But here we're just going to start with something simple, which is binary cross entropy. So let's say we want to classify these tweets into either positive or negative. Then what we're going to do is we're going to have the model output the single score, and we're going to interpret it as being a probability of the positive class. So I guess maybe the neural network doesn't necessarily care about how we interpret it, but we have to make sure that it's between 0 and 1, because then it can't possibly be, you know, valid. So here what you do is you use this activation function, which is called sigmoid, and this will just ensure that your outputs are between 0 and 1. Okay, so now we can start interpreting this as a interpreting the output of the network as a probability. And so now we assume that we have some label. So the label will either be 0 or 1 in our training data. And the question is, how do we form some loss function? So this binary cross entropy loss looks like this on the right, and you can see the loss written there below. And the kind of easy way to, or like a good way to look at this is just look at one thing at a time. So let's first suppose that y equals 1. Then what happens is this term here will be zeroed out. So we could basically ignore it. And then this term here will be 1 times log p. So it's basically saying that the loss is minus the log probability. And so what that's saying is if we want to minimize it, then we want to push the probability up, so towards 1. And so here we could see if the label is 1 and our model's already assigning some high probability, then the loss will be kind of small. Here, if the model's predicting a small probability, then the loss will be high. So it'll kind of encourage pushing the probability towards this 1 class. Now, if we suppose that the class is 0, then you could kind of go through the same process. So this one will cancel out. So we can only look at this. And now it's log of 1 minus the probability. And this will basically encourage the opposite behavior. So it'll encourage the model to set the probability to 0, which is the label. So yeah, kind of it can be pretty intuitive when you kind of step through it. Again, it's encouraging the model to assign probability equal to the label. So then you could consider, what if we have multiple classes instead of just 1 and 0 or binary? So this will be the multi-class cross entropy. And so here, let's say we want to classify tweets as positive, neutral, or negative. But really, it doesn't have to be 3 classes. It could be 50,000 if you wanted. Oops. So now our model will output this vector, and it'll be a probability vector. So to be a probability vector, what this means is the sum has to be 1, and then the numbers have to be individually non-negative. And so the way one way to do this is to take your scores and then use the softmax function. So we briefly mentioned the softmax in last class. But here it is. And again, the one reason to use this is that it results in a vector which is in the probability simplex. So it's it sums to 1 and everything is non-negative. Okay, so yeah, this is the form of the softmax function, and if you haven't seen it before, then yeah, be sure to review that because the softmax will appear everywhere, and you kind of want to be know what it is. Now, what we're going to do is we're going to imagine that this ground truth label, so in our data, is actually a probability vector as well. So when you think about it, these one hot vectors is actually a probability vector. It sums to 1, and everything is non-negative. So we can kind of view it as a probability distribution. And now you can ask a kind of clever question, which is like, okay, what if the goal now is to just make our model match this distribution, so match the data? Then yeah, that's a pretty good criterion, right? So that's the idea of what the cross entropy loss will do. So here it is written out here, and you can see that basically we go over each class. So here we'll have 3 classes. And then again, you have this thing where all the zeros will zero out. And so you'll just end up with one term, which is the class is 1, So you'll have log probability of the class that's in the data. And then if you take minus of the log, and you're trying to minimize, then it basically corresponds to maximizing the probability of this particular class. Okay, so if it's hard to like interpret the words or something, then it's worth spending some time with this. Again, the basic idea is it'll zero out everything, and then this loss will encourage increasing the probability of this class that's in the data. That's the really core idea. And actually, there's a whole slide about this. So suppose that your model assigns high probability to the correct class. Then the log probability will be, then, P for this class will be about 1. The log probability will be about 0. So you'll have a small loss. Conversely, if the model assigns low probability to the correct class, then you have this very large loss. Okay. So that's the cross entropy loss. And so now we can consider one more thing. And this is pretty interesting. So this is basically saying that what this cross entropy loss does is it actually causes the model to fit this target distribution or target probability vector. So there's this divergence called KL divergence, and this is basically the formula. And so the question is like, suppose we want to minimize the KL divergence between the model's distribution, so the model's kind of vector, and the target distribution. Then this is just writing out the definition of KL divergence. Now this is just expanding the terms. And then what you can observe is that if you're minimizing this P2, then this term over here just has P1 in it. It doesn't have P2 anywhere. So you can just ignore it. And so now you end up with this term right here. And I've actually seen that before. It's actually the cross entropy loss. So basically it's saying that minimizing this cross entropy loss is equivalent to minimizing this divergence between 2 different distributions. Okay, and then here's the concrete example that we were looking at. So again, this is a really cool idea, and if it doesn't like kind of resonate yet, then I'll bring it up again, especially when we talk about language models, because it'll turn out that the way we train language models, you can also interpret it in this way, where the model is kind of learning to fit some target distribution. So it is a pretty cool idea. And so yeah, I'll mention it a couple other times. Okay, so then if you think about how to implement this, sometimes I mean nowadays, you know, this loss, as I mentioned, is very common. So you might see it implemented in PyTorch. And then you might see the implementation and it kind of doesn't look like the you know, it doesn't look like the equation. So yeah, what you have to do is kind of step through and make sure you understand this. Essentially, it's taking advantage of what I was saying before, where all of the terms are zeroing out except for the target class. So then basically the loss ends up being selecting your model's probability of the target class and then minus that, or minus the log probability. Okay, so it can look a bit tricky, but you know, this is how you can implement this cross entropy loss. And again, this will be implemented in the notebook if you want to take a look. Now, as with everything, like suppose you're spending millions of dollars training a model with this loss, then the actual implementation they're using probably looks different because they want to make it efficient and stuff. But yeah, it's good to understand this one. Okay, any questions about that before I move on? Okay, cool. So now the next step is we want to calculate these gradients of the loss function. So here I have to be cognizant of time. But basically here you can go through and I mean in the old days, what you'd have to do is you'd have your neural network architecture and then you have to by hand calculate what is the gradient or what is the derivative, you know, with respect to each parameter. And then you implement that gradient and then you can run the optimization. So nowadays, as I'll mention later, we have these automatic differentiation packages. But it's good to do kind of one of these exercises to understand how this works. So here, like suppose our model is the sigmoid function of wx plus b. And then let's say we're using this binary cross entropy loss. Then what we want to do is we want to find what is the derivative of the loss with respect to this parameter. So partial L over partial W. And then the key idea that is taken advantage of in deep learning or this backpropagation is this chain rule. So you could decompose it into these three different parts. And now you can just go through and compute each one of these parts one by one. So if you were to compute this partial L over partial P, then it is this. And then if you do these two, they're this. And maybe just make sure I get through everything. I won't step through all these, but then, you know, you can multiply these together and you get this gradient here. And so now the idea is now we have some direction that we can move our parameters in. And it'll be what's shown here. So P minus Y times X. And this one actually turns out to have a pretty intuitive interpretation. But maybe let me make sure I get through everything. So now once we've gotten the gradient, then we can use this gradient-based optimization. So the standard, the kind of most basic algorithm is the stochastic gradient descent. And so we'll get this gradient of loss, like the one that we just computed on the slide. And then we will just do gradient descent, which means subtract the gradient. And then this eta here is what's called a learning rate. So the learning rate will just control how large of an update you do on each step, with each gradient. And then of course, this is a really important part, and it could affect how practical it is to train different models and things like that, and the speed of training. And so there's been a lot of research on this, and better optimization algorithms have been developed. So I'll talk about one that's used frequently called Atom, but I think I put it in next lecture just because there's already a lot in this one. So then what you end up seeing if you like use PyTorch and don't implement it all yourself, then you'll see this kind of standard training loop. So here you can set up the loss. You can set up the optimizer. So this is using stochastic gradient descent, or SGD. And then you loop through your data. You pass it through the model. Typically, these scores are called logits. Then you would compute the softmax and compute the loss. And then you can kind of perform the optimization. So actually perform the update that we saw on the previous slide. Okay, and so although I went through it a bit quick, now at least I've introduced everything that's kind of involved in doing this. And so again, you can go through and run the take a look here, see this concrete example where we have actual data, print things out if you don't see what's going on, and make sure that you kind of understand this. So this is yeah, and then you can classify sentences like, I'm learning so much in advanced NLP, positive, yes. So finally, yeah, as I mentioned, there's a lot in this lecture because hopefully at least some of it is a review. So right at the end here, I'll quickly just talk about this backpropagation and automatic differentiation. So nowadays we don't really typically compute these gradients by hand. You'll use a system, like PyTorch, and behind the scenes it'll be doing all of this bookkeeping to compute the gradients. And so really in their modern form, this neural network is really one of these computation graphs. So here we start off with some expression like our data x, and then you can basically represent the forward pass through the network as this directed acyclic graph. So you can perform different operations, like here we're performing the transpose. Yeah, so here we have this operation, and the kind of incoming edge will be the argument. So here it's f of u, but then you'll use the argument x, to perform the computation. And then if you look at, how you would implement one of these, then basically you have to ensure that each node can do two things. It has to be able to compute the value of the function, and then it also has to know how to take the gradient with respect to each input. Okay, so oops. So what you have here is you have this kind of chain rule that we're going to take advantage of. And if kind of each node knows how to compute its own gradient, then you can like take the kind of incoming gradient and chain them together, and then ultimately get this kind of full the gradient of like things deeper in the network. so just to show this here, this expression is now getting more complicated, and here's the graph that corresponds to it. Now we have our output, and we can get this. So this will be called the forward pass, and you can see here that we're going to have to do this bookkeeping to kind of keep these intermediate values. And the reason is that for this back propagation, you now want to compute the gradients without kind of recomputing everything. So here, again, we're going to start and compute this local gradient. Remember, we said that each node knows how to compute the local gradient. Then we're going to pass that down, and now you can multiply this kind of incoming gradient with the local gradient. Similarly, you can do that for the next node, and over time you can get the gradients associated with every node in the graph. So I'm going through this very fast. So if you want to know the details, refresh yourself on them or learn them, you'll probably have to take a closer look at this to really kind of internalize it. But here, this is the kind of key idea behind being able to automatically perform the computations of the gradients, which is then used to update the model through gradient descent. Okay, so nowadays we have these different neural network frameworks. So PyTorch, TensorFlow, I think use less nowadays, and JAX. And this comparison slide was made by Graham. Yeah, PyTorch, I guess, is probably the most widely used in NLP. And they do have different kind of properties, especially like TensorFlow versus PyTorch. PyTorch was designed to have this dynamic execution. At the time, we didn't really have that. You'd have to kind of declare the graph upfront. Whereas if you declare the graph upfront, then you can compile it and optimize it and things like that. So like the dynamic can be more flexible. You can put in like debug statements even if you want. And then this was the, I guess, opinionated part, which is the most vibrant ecosystem is around PyTorch. And yeah, I guess your first homework will be in PyTorch. So then this is just classifying using the model that we trained. And yeah. So to recap, we covered a lot today. So I talked about tokenization and subword models. So how you represent the tokens, or how you kind of represent them as input. Then we talked about representing them as learned continuous vectors and these simple neural network architectures. And then went into some of the details of choosing a loss function, constructing this graph, and performing gradient-based optimization. So that's it for this class, and I guess we're right at time. So thank you.